taking a look at molecule polarity. So a few questions here for you guys to try on your own. I'd recommend pausing the video and then coming back. So water is polar. What properties of water are related to its polarity? Things like it has good surface tension. There are bugs that could walk on water, and when you put drops on something, they hold themselves quite well. You can also overfill a glass of water and make it bubble up top a little bit. It has the ability to stick to itself, so cohesion, and it's able to stick to other substances, so adhesion. Both are really important properties for plants to utilize water. And the last is that it's a really good solvent. It's one of the most popular solvents. A lot of things are dissolved in water. What do we know about the solubility of polar and nonpolar compounds? Some people may have heard the saying, like dissolves like. So what this means is polar substances dissolve polar substance. And nonpolar dissolves nonpolar substances. So just a quick comparison, what is bond polarity in comparison to molecule polarity? So bond polarity is what we talked about in the previous video, and it's a difference in electronegativity resulting in an uneven distribution of electrons between two elements. So this was the unequal sharing. And this made a polar bond. The molecule polarity contains an unequal distribution of electrons throughout an entire molecule, not just a bond, due to an asymmetrical shape and or a difference in bond polarities throughout. So this is like adding up all bond polarities and considering the entire molecule. So in bonds, we're just looking at each individual bond. In molecule, we're looking at the whole thing altogether. So there's two ways to determine the polarity of a molecule. The better way to do it, the more chemistry way to do it and scientific would be this first method. And I've got a little cheat sheet for a second method. So we're going to use bond polarities and the Vesper shape. So the steps to doing this is we need to draw an appropriate Lewis dot diagram for our molecule and then draw a stereochemical representation of the molecule. This is our Vesper shape. All right, so once we have those two things, we're going to determine the bond polarities of each bond and indicate them using a bond polarity arrow, and that's this one. From there, we're going to decide if the central atom would be pulled or moved in a tug of war between outer atoms, considering that the tug of war can happen in 3 dimensions. So for instance, we could have our central atom and let's say 3 bonded atoms here. They may not all be the same. Let's actually change one, and I'll say that this is Y. All right, I'm going to draw in some bond polarity arrows, just making this up. If these two are the same element, they will have the same arrow. Okay, so the same electronegativity difference. However, because this is a different element here, it may have a different electronegativity difference. So let's add this one smaller to represent a smaller delta En. And I'll draw it in the opposite direction. Maybe Y is more electronegative than A. All right, if we consider this as a tug of war, think about what's happening. So these two that are the same are pushing in on A together. If this was pushing in the same amount, A wouldn't move, and we could say that this is nonpolar. However, these two are pushing in on A, and they don't quite cancel out. Together they push A a little bit this way. And then we have this one, and if it's connected to A, it's pulling this way. So in general, A will move, and we can say that this is a polar molecule. If something doesn't have any bond polarity arrows, maybe it's a non-polar bond all the way around, it's non-polar. And we'll see some instances maybe where they cancel out. Let's go through a few examples here. So BCl3. To draw its Lewis dot diagram, let's consider the number of valence electrons. So boron has 3 plus 3 times 7 from chlorine, and we get 24 electrons total. So we're going to put boron in the middle, and I'm going to draw 3 bonds to chlorine. I've used up 6 electrons. I'm left with 18. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I'm all out. And we have to ask ourselves, is everybody happy? Well, it kind of looks like boron's not. It only has 6 electrons around it. However, boron is happy this way. Boron only ever wants 6 electrons around itself. So I've also drawn the stereochemical representation here because this is an AX3 representation. It's trigonal planar. So each of these are 120 degrees, the bond angles, and so they're evenly spaced out here. All right, looking at electronegativities, boron has an electronegativity of 2.0 and chlorine is 3.2. So I'm going to draw in some bond polarity arrows, and they will be pulling towards chlorine because it's the more electronegative atom, and they would all be approximately the same length because the difference in electronegativity between boron and chlorine in each case is 1.2. So they're all the same. All right, so this is like a tug of war pulling equally in a bit of a peace sign shape. And if that's the case, this central atom, boron, is not going to move. Therefore, it is non-polar. All right, let's take a look at the next one. PCl3. Phosphorus has 5 valence electrons, and each chlorine still has 7. So this time we have 26 electrons. Phosphorus is our central atom, and I'm going to connect all of my chlorines that used 6 electrons, so I have 20 left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I put the last 2 on that central atom. Now, this shape is AX3E, and this is trigonal pyramidal. All right, so let's draw that. So P is in the center, and I have 1 down here, 1 out of the page here, and 1 into the page here. All right, so now that we have our diagram here, remembering these angles are 107.3 between them. And even this chlorine to this chlorine around the backside is 107.3. They're all equal. All right, phosphorus has a electronegativity of 2.2 and chlorine is 3.2. So fairly close to what we had before. The change or the difference in electronegativity is 1 here. So this is a polar bond, and to draw those bond polarity arrows, we would draw them approximately the same size on each bond here, pulling towards chlorine. Now, again, it's tricky without the molecular models, but recognize that this is like a pyramid where phosphorus is at the top. It's harder to see in this case, but phosphorus is at the top and each chlorine is pulling downwards equally. That would be along the back side of our pyramid. If that's the case, phosphorus doesn't have anything pulling upwards here because it's filled with a lone pair at the top. So without that doing any sort of push or pull, phosphorus is going to move down with our chlorines. So it will be pulled a little bit by our chlorines. Therefore, this is a polar molecule. Last one, CCl2H2. I should have written that actually, CH2Cl2. H's come right after carbons. No big deal, same thing though. 4 valence electrons plus 2 times 1 plus 2 times 7, 14, 18, 20 electrons it looks like. So we'll put carbon in the middle. It has the most bonding capacity. And we'll put chlorines. I'm going to draw it like this. If you draw yours a little bit differently, maybe you put 2 hydrogens on one side and 2 chlorines on the other side. That's the exact same thing, no big deal. All right, with that, we have used 8 electrons, so we still have 12 to put in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm all out, which is fine. Hydrogen is good with just 1 bond. Looks like chlorine is happy. Chlorine is happy and carbon is happy. So this is an appropriate drawing. This is an AX4, so a tetrahedral. Therefore, we need to draw it in 3 dimensions as well. So carbon, and it doesn't matter where you put anything around the carbon. So I can put H's together or apart. Again, because these are not actually 90-degree angles, they end up being 109.5 between everything. So it doesn't matter how I draw it now. I'm going to put my H's and maybe my Cl's. Okay, bond polarities. Let's look up our electronegativity. So carbon is 2.6, hydrogen is 2.2. So carbon is a little bit more electronegative, not by very much though, so very slight pull inwards towards carbon from each of those hydrogens. Again, the difference in electronegativity here was 0.4. Carbon to chlorine. Chlorine, again, is 3.2. So the pull on chlorine will be a little bit larger and is pulling towards those chlorines. So, the difference in electronegativity here was 0.6. Again, I can kind of draw this as a triangular pyramid, and I'll just do this, where carbon would be sitting here, and the way that I've drawn this, chlorine is a little bit behind us, there's one coming out towards us, there's a hydrogen here, and then there would be a hydrogen above it. Now, just looking at our bond polarity arrows, this one's pushing in a little bit, and so is this one. So technically, our chlorine would be moving this, our carbon would move this way if there was nothing else bonded to it. However, we have these chlorines, and they are pulling downwards a little bit and towards the side that carbon was already being pushed towards. So carbon moves in this case, and this is considered a polar molecule. This seems like a lot of work, and it is, but it is the most scientific way of describing this to decide if something is polar or non-polar. Now, not everybody likes that, and it can be a little bit tricky. So I have this little flow chart in your notes, and you'd want to fill it out here. We'll go through it. And it's just simplified all of this, so we wouldn't have to do that entire process above. What we do need, though, is we need a Lewis dot diagram, and from that Lewis dot diagram, we need to decide bond polarities. Okay, so we don't need Vesper, and we don't even need to draw it in Vesper. Then we're just going to go through this flowchart and ask ourselves these questions. Does the molecule have polar bonds? Yes or no? If it doesn't have any polar bonds, it can't be a polar molecule, and it is overall going to be non-polar. If it does have polar bonds, we have a few more considerations to make. Are there lone pairs on the central atom? So this is not talking about peripheral, it is just that central atom that we are looking at. If there are lone pairs, it is polar. And that comes back to the case of PCl3. There's nothing pushing up or pulling down on the top where that lone pair had taken away a bonding pair. If there are no lone pairs on the central atom, we might be able to get away with that. And we'll have one more question. Do all bonds on the central atom have the same change in electronegativity? So the same bond polarity. Are they all pushing with the same amount or the same value, or are they all pulling with the same value? If there's both a push and a pull, those are unequal. So remember that. Okay, so if they are all the same, it is a nonpolar molecule. All of those pushes or pulls cancel out. If they are not, kind of like our last example there, CH2Cl2, it is a polar molecule. I have lots of examples here. I'm just going to do a few of them, and then you can double check on the notes. I do have my completed notes up for you guys to take a look at. All right. I'm going to do pH3, this one, and maybe C2H6. So let's draw a diagram for pH3. I'm just going to hustle through these. Maybe go ahead and draw your Lewis dot diagrams, and you can double back on these if you need the practice. So we have pH3 and CH3. I didn't really give myself a lot of room here. Cl. The last one is C2H6. All right, so using bond polarities, I'm going to double back to our, I said I'd do ammonia too, sorry. All right, we'll go back to pH3 here. So pH3, phosphorus has a 2.2 electronegativity, and hydrogen also has a 2.2. So there is no bond polarity arrow here because the difference in electronegativity is 0. All right, so let's start at the top of our flow chart. Does the molecule have polar bonds? No. Therefore, it's a nonpolar molecule. Okay, let's take a look at CH3Cl. C to H has a very small bond polarity. The difference in electronegativity is 0.4, and it is slightly pushing towards carbon in each case. Chlorine is 3.2, and again, carbon was 2.6. So chlorine is going to pull a little bit here. So we'll start at the top of our flow chart. Does the molecule have polar bonds? Yes, it has polar bonds. Are there lone pairs on the central atom? No, there are no lone pairs on the central atom, which is carbon. Do all the bonds on the central atom have the same electronegativity and push-pull? No, I mean, 3 of them are the same and pushing in, and then there's another one that's slightly different, a little bit larger, and pulling outwards. So no, it does not. Therefore, this is a polar molecule. All right, ammonia here, nitrogen is 3.0 for an electronegativity, and hydrogen is 2.2. Therefore, in each of these bonds, it will be pulling inwards on those electrons slightly. Sorry, I'm not doing a very good job of making my arrows the same size. There we go. Okay, starting at the top, does the molecule have polar bonds? Yes. Are there lone pairs on the central atom? Yes. Therefore, this is polar. So that was, a yes and then a no. And that was just straight up a no. All right, C2H6. If we look here, hydrogens are an electronegativity of 2.2 and carbon is 2.6. Now these are like very slightly polar bonds, so we'll just draw those in. All right. Now this one's tricky. We kind of have to use our Vesper in this case because there are 2 central atoms. Okay. So I'm going to quickly draw this one out. we have two central atoms, and each of them are tetrahedral. So what I do is I connect my central atoms. I'll start this over, sorry. I'm going to start with one, and I'm going to draw the bond in the plane of the page, and I have to connect my other central atom that way. I don't want to use any of my dashes or dotted lines to connect central atoms. All right, I'm just looking at our first carbon here, and I'm going to draw the rest of a tetrahedral around it. And I'm going to draw the other one here kind of upside down, if you will. Just if you turn your page around, this would make the rest of the tetrahedral shape. All right, H is in here. Now, each of these are pushing inward ever so slightly. And it's a little hard to tell here, but remember that these are in 3 dimensions. And again, because we don't have molecular models, it gets a little bit tricky. So this is really a challenge question, in case you haven't noticed, because there's 2 central atoms. Okay, looking here, this hydrogen would be pushing on carbon, and all of the rest will be pushing on carbon. So carbon will slightly want to move this way. But all of these guys are pushing on their carbon, and it wants to go this way. And so they will be pushing inwards on one another in an equal and opposite fashion, and they will cancel out. So that's one way to look at it. Also, this hydrogen and this hydrogen, sorry, I wanted to keep that color-coded, are in the same plane with the same electronegativity pushing on one another, so they would cancel. Then this hydrogen is opposite of this hydrogen, and they cancel. And last but not least, this hydrogen is opposite of this hydrogen, and they would cancel. And again, because we have 2 carbons in the middle, they are the same electronegativity. There's no bond polarity. Again, this is a non-polar molecule, and it's tricky to see, but anything with just C's and H's, there's nothing else, is non-polar. So I could connect 16 carbons. I mean, I'm not going to draw that, and H is all the way around this in a Lewis dot diagram. If all the little dashes were connected to an H, this would be non-polar. It would take a lot of work to draw it like this. So just C's and H's, where this can be any number and this can be any number, will be non-polar. As soon as you start, oh my goodness. As soon as you add another element here, that changes the non-polar status. We can't say that then. We'd have to draw it out. All right, there is some practice in your Lewis structures worksheet. Finish it all up, all but polarity. I want you to do the molecule polarity now. And there's some extra questions in your textbook if you're looking for more practice as well.